Welcome to the deep dive. Today, we're really embarking on a journey. We're going to explore this powerful partnership forming between artificial intelligence and, well, the fundamental world of physics.
That's right.
You, our listener, shared a fantastic resource with us, Artificial Intelligence in Physics.pdf by Mohammed Medhat Gaber. And our goal is really to uncover the most groundbreaking, the most insightful ways AI is changing how we understand everything. You know, from tiny particles right up to the whole cosmos.
Yeah, it's like AI is giving physicists these incredible new tools, almost superpowers.
Exactly. Superpower.
And this source, it lays out such a detailed picture of how these fields are converging. It's not sudden either.
No.
No, the book traces it back, starts with early computers just crunching numbers for physics calculations. Then it moves through machine learning popping up in particle physics way back in the 70s.
The 70s, wow.
Yeah, and neural networks in the 80s for interpreting data. Then the 2000s, the big data era, right? Machine learning became crucial for things like the Sloan Digital Sky Survey, these huge astronomical projects.
Okay.
Then the 2010s brought the deep learning revolution, applied to analyzing telescope images, quantum simulations. It even played a part in finding the Higgs boson at CERN.
Higgs, right.
And now today, it's deeply integrated. Quantum computing, finding new materials, cosmology. It's everywhere.
Okay, so let's frame this for you, the learner. Your mission listening in today is to really grasp how AI is becoming this super sharp lens, but also a tireless assistant for physicists. It's tackling these huge challenges, right? Like making sense of really complex systems, nonlinear stuff, sifting through data with just like tons of dimensions.
These that are hard to even visualize.
Exactly, and overcoming computational limits, trying to simulate the whole climate or how galaxies form, plus dealing with messy, noisy, experimental data.
Yeah, real-world data is rarely clean.
And just the scale, like the Large Hadron Collider. So, yeah, get ready for some real aha moments here. Let's kick things off with something truly staggering. The data, just the sheer amount of data modern physics generates.
Indeed. The scale it's hard to comprehend sometimes.
Yeah.
The source points out, experiments like the LHC producing petabytes of data.
Petabytes.
And the upcoming Square Kilometer Array telescope. That's projected to generate exabytes.
Exabytes. Okay, what does that even mean in real terms?
Well, think of a petabyte as maybe 1 million HD movies. An exabyte is 1,000 times that. Traditional analysis methods they drown in that. They can't keep pace.
Exactly. Like trying to find one specific snowflake in a total blizzard. But this is where AI shines, doesn't it? It's this incredibly efficient data detective.
That's a great analogy.
It sifts through all this stuff, finds patterns, trends, maybe anomalies humans would just miss. And the source mentions techniques like clustering and dimensionality reduction. How do those help cut through the noise?
Certainly. So clustering. Think of it like AI automatically grouping similar bits of information. In particle physics, after a collision at the LHC, you get this spray of particles hitting the detector, right? Clustering helps figure out which hits likely came from the same particle, helps reconstruct what happened.
Okay, got it.
Dimensionality reduction. That's more like taking a super complex data set, loads of different measurements, and finding the maybe handful of key underlying factors that explain most of what's going on.
So simplifying it, basically.
Yeah, simplifying it without losing the important stuff. Like finding the few key questions in a huge survey that capture the core opinions. It makes the data manageable, reveals connections you wouldn't see otherwise.
Okay, now this is where it gets really interesting. The source gives specific examples of this data detective work. High-energy physics first. AI algorithms are apparently crucial for track reconstruction and particle identification. That sounds fundamental.
Oh, it absolutely is. Track reconstruction. That's piecing together the paths particles take through the detector. Like analyzing firework trails to see where they started and how they burst.
Okay.
AI analyzes the signal patterns left behind and rebuilds those tracks very precisely. Then, particle identification is figuring out what particle made that track.
How does it do that?
Based on how it interacts. Did it lose energy fast, curve sharply in a magnetic field? AI learns the signatures of different particles. And like the source says, this was vital for the Higgs boson discovery.
Right, you mentioned CERN.
Yeah, they had to sift through just unbelievable amounts of collision data to find that specific decay pattern signaling the Higgs. AI made that possible.
And it's not just the super small. AI is helping with the super vast, too. Gravitational wave astronomy. The source mentions AI, especially convolutional neural networks, helping detect these incredibly faint ripples in space-time, from black hole mergers and stuff. That sounds like hearing a pin drop during a rock concert.
That's a pretty good way to put it, yeah. These signals are often incredibly weak, just buried in noise.
Noise from what?
Oh, anything. Ground vibrations, electrical interference, loads of things. But AI, especially these convolutional neural networks, they're really good at finding subtle patterns in noisy images or data. They can be trained to pick out the specific chirp of a gravitational wave.
Wow.
And that's transformative. It lets us hear much fainter, more distant events. It's a whole new way to observe the universe, studying black hole collisions.
Yeah.
We're not just seeing light, we're feeling space-time itself vibrate.
So AI is this amazing data detective sorting through these mountains of information. But it's not just looking backward at data, is it? It's also looking forward, acting as a kind of super-powered simulator.
Exactly. If you think about it, many physical systems are just incredibly complex. Turbulent fluids, air or water,
Right.
or how billions of atoms interact to give a material its properties.
Right.
Traditional simulations, they often hit a wall, they just need too much computing power, take too long.
Like trying to predict every single falling leaf in a forest for a whole season. But AI helps with surrogate modeling. Can you break that down?
Okay, imagine you have a really complex, slow simulation, maybe modeling a new solar panel material. Running the full thing takes days, right?
Mm-hmm.
A surrogate model is like an AI-powered stand-in. You train the AI on results from the slow, detailed simulation. Then the AI can predict outcomes for different conditions much, much faster, but still pretty accurately.
So it's like a quick emulator.
Exactly. An emulator lets scientists explore way more possibilities, optimize designs faster, cheaper. It's a super fast AI version of the original simulation.
That sounds incredibly useful, speeding things up like that. The source also mentions generative models, GANs and VAEs. How do they fit into this simulation picture?
This is fascinating. Generative models, like Jan's generative adversarial networks, they basically learn the underlying patterns from existing simulations. And then they can generate new, realistic-looking simulations themselves.
Like completely new ones.
Yeah. So you could train a Jan on galaxy formation simulations. Then it can generate artificial galaxies that look statistically like real ones. This synthetic data is super useful, maybe for training other AIs or testing theories.
And VAEs.
Variational autoencoders, VAEs, they work a bit differently. They learn a compressed version of the simulation data, like the essential features. Then they use that compressed version to generate new, similar data. It's like learning the key ingredients and recipe, then making variations.
And it gets even more sophisticated with physics-informed neural networks, PIM-MENS. That sounds like they're not just learning from data, but learning the actual rules of physics.
That's exactly the key insight there. PIM-MENS are powerful because they directly bake in the known laws of physics, the equations for fluid flow, gravity, whatever, right into the AI model.
So the AI has constraints.
Precisely. It's not just trying to fit data points blindly. It has to obey the fundamental physical principles we understand. This helps solve complex problems and ensures the answers are physically meaningful, not just mathematically plausible.
Okay, so AI helps analyze data, simulate systems, but could it go even further? Could it actually help us discover totally new laws of physics? The source hints at this, calling AI a theoretical assistant. That sounds, well, almost sci-fi.
It does feel a bit like that, doesn't it? But it's becoming more real. A key technique is symbolic regression, often using genetic programming.
Symbolic regression.
Yeah, basically, it lets the AI search for mathematical equations that best fit experimental data without us telling it what kind of equation to look for. Imagine feeding an AI planetary motion data and it just figures out Newton's laws of gravity on its own.
That's mind-blowing. Like AI becoming its own theoretical physicist, finding things humans missed.
Potentially, yeah.
Yeah.
And the source also mentioned AI helping with really complex stuff like quantum field theory, string theory. These are areas that challenge even the brightest human minds.
Right, notoriously difficult.
Exactly. So in lattice QCD, that's our best tool for understanding the strong nuclear force holding atoms together. AI is speeding up those incredibly demanding simulations. And in string theory, with its huge landscape of possible solutions, machine learning helps navigate that space, find solutions that might actually match our universe.
Like an AI research assistant exploring mathematical jungles.
Kinda, yeah. Exploring possibilities beyond our intuition sometimes.
And even the nitty-gritty work of theoretical physics gets a boost. Improving computational algebra systems, automating theorem proving, simplifying complex equations.
Precisely. It frees up the theorists, right? AI can handle some of the heavy lifting, the computation, the symbol manipulation, letting humans focus more on the big conceptual leaps.
It's about augmenting human intelligence then, not replacing it.
That's the key idea, yes.
It really seems like AI is touching every part of physics,
Yeah.
including the practical side experiments. It's not just analyzing data after, it's getting involved during the experiment.
That's absolutely right. Experimental physics is really changing because of AI. Take automation, for example. Robots, guided by AI. They're doing routine lab tasks, even handling hazardous materials, controlling experiment parameters, collecting data with superhuman consistency.
Makes sense. Like robots in manufacturing, but for science labs. And the source mentions real-time data acquisition and processing. That must be critical with those data floods we talked about.
It is vital. When data pours in that fast, analyzing it as it arrives is key. The source mentions edge computing, doing AI analysis right there at the experiment site.
Why is that important?
It allows for immediate feedback, immediate adjustments, crucial for controlling complex systems, like, say, a fusion reactor. You need to react incredibly fast to keep things stable.
And it's not just speed and automation. AI helps get more accurate results too, better measurement precision.
Exactly. AI is significantly boosting precision. Neural networks, other techniques, they're filtering out noise. Remember the pin drop in the rock concert. And improving instrument calibration. It leads to more accurate, more reliable results, whether you're detecting faint gravitational waves or, looking at medical images.
Now let's dive into a really fascinating zone. AI meets the quantum realm. Quantum physics is already pretty weird. What happens when AI gets involved?
Well, what's really exciting is it's a two-way street. Quantum machine learning is exploring how future quantum computers, with their unique power, could accelerate AI algorithms themselves.
Okay, so quantum computing could make AI even smarter, but how is AI helping us build quantum computers now? Because that sounds incredibly tricky.
It's a massive challenge, absolutely. And AI is already proving invaluable there. The source highlights things like quantum state estimation,
Meaning?
figuring out the exact state of the qubits, the quantum bits. They're incredibly delicate. AI is also crucial for error mitigation and correction. Quantum computers are super sensitive to noise, so correcting errors is essential for them to be reliable. And AI, using methods like neural network quantum states, is even helping simulate complex quantum systems that are just too hard for regular computers.
Wow. It feels like we're just scratching the surface of what AI and quantum can do together. Okay, let's shift focus again. Go to the grandest scale, the cosmos. AI is playing a huge role in mapping the universe, right?
Absolutely. In cosmology, astrophysics, AI is becoming indispensable. Just think about the sheer flood of data from telescopes constantly scanning the sky.
Right, those massive surveys again. How's AI sorting through all that?
Well, deep learning is used a lot, classifying galaxy shapes as a spiral, elliptical, irregular, distinguishing stars from distant galaxies in those huge images, even spotting transient events like supernovae almost in real time.
Spotting them as they happen.
Yeah, and as we mentioned, analyzing those subtle gravitational wave signals from LIGO and Virgo relies heavily on AI, too.
And understanding the universe's structure, like dark matter and all that, AI helps there too.
Yes, it helps analyze weak lensing data. That's where you look at how dark matter's gravity subtly bends light from background galaxies, letting us map where the dark matter is.
Okay.
And AI is also used to create fast emulators of those super complex cosmological simulations that model the universe's evolution, help scientists test different theories much more quickly.
And finally, finding planets around other stars, exoplanets. AI is involved in that search too.
Indeed. It's key for sifting through data from missions like Kepler and TESS, looking for those tiny dips in starlight when a planet crosses in front.
The transit method.
Exactly. And AI also helps analyze the light filtering through exoplanet atmospheres. That gives us clues about what they're made of, which is critical for figuring out if a planet might be habitable.
It's truly amazing how deeply embedded AI has become, across the board, really. So wrapping up, what are the main takeaways from this deep dive into AI and physics?
Well, I think for you, the learner, the big picture is AI's incredible ability to handle these massive, complex data sets, to find patterns humans might miss, to simulate really intricate systems,
Yeah.
and even to help develop new theories. It's just fundamentally changing how physics is done.
Yeah.
It's letting physicists ask questions that were just too hard before, accelerating discovery everywhere.
And as AI keeps getting better, maybe even merging with quantum computing down the line, it does make you wonder, doesn't it? Are there limits to what we can discover? Could AI lead to breakthroughs we can't even conceive of right now? Yeah, pretty provocative thought.
It really is. And look, this deep dive, we've only scratched the surface, really. It's such a fast-moving field.
Yeah.
So we definitely encourage you, the learner, if something sparked your interest, dig deeper.
Yeah.
Look into AI in cosmology papers or quantum machine learning. The resources are out there, and it's constantly evolving.
Absolutely. Well, thanks for joining us for this deep dive into the fascinating world where AI meets physics. Until our next exploration, keep wondering.